Hello everyone, we are Ashish
And Vedant.
and we are going to elaborate our project entitled ECG Transmission and Monitoring. The mentor of our project is Dr. Lalita. So, what was the motivation behind our project? So, cardiovascular diseases are the leading cause of death worldwide, accounting for 32% of global deaths in 2019. This translates to an estimated 17.9 million deaths, with 85% of these deaths being attributed to heart attack and stroke. ECG monitoring offers a non-invasive diagnostic tool that could aid in the detection of cardiac abnormalities and provide opportunities for research into cardiac function and disease. Additionally, these circuits can serve as an educational tool for medical students and healthcare professionals interested in learning more about ECG signals and their applications in diagnosing and treating cardiac conditions.
Now let's see what are the literature survey we have done for this project. Here are some resources and books related to ECG monitoring systems and cardiac signal processing. The first one is Advances in Cardiac Signal Processing by U. Rajendra Acharya. This book provides an overview of latest developments in cardiac signal processing techniques and their applications in clinical diagnosis and treatment. Wireless ECG monitoring system design, construction, and analysis. This paper describes the design and implementation of wireless ECG monitoring system, includes the hardware and software components. Electrocardiographic circuit design by Nathan M. Kisto. This paper discusses the design of low-cost ECG circuit that can be used for monitoring patients in hospitals or at home. ECG monitoring system. This paper describes the development of ECG monitoring system using a microcontroller and Bluetooth technology, which allows for wireless transmission of ECG signals to smartphone or tablet. Now let's move to the preliminary design of our circuit. The first one is the instrumentation amplifier. We built an instrumentation amplifier in order to amplify the small amplitude measured from the body. Using two amplifiers in our first stage will allow us to cancel out the noise created by the body, which will be the same for both the electrodes. We will use two stages at about equal gain. This protects the user if the system is connected to a person by preventing all the gain from happening in one place. Since the amplitude of our ECG signal is between zero point 0.1 to 5 millivolt, we want the gain of the instrumentation amplifier to be 1000. The instrumentation amplifier shown here. The op-amps 1 and 2 are non-inverting amplifiers and op-amp 3 is a difference amplifier. These three op-amps work together, form an instrumentation amplifier, and
We
this
did
this is the calculations we did for our instrumentation amplifier. This is the continuation of the same calculations we did for the instrumentation amplifier. Now let's move on to the next stage of our design, that is a notch filter. We have used a notch filter to remove 50 Hz noise present in all power supplies. We set the quality factor Q to be 8, which will provide an acceptable filtering output while keeping the component values in a feasible range. We also set the capacitor value to be zero point 0.1 microfarad so that the calculation affect the resistors only, and the resistors value that we got are shown in the calculations on the right side of the slides.
Coming to the next stage, we have a low pass filter. The next stage of this device is an active low pass filter. The ECG signal is made of many different waveforms, which each have their own frequency. We want to capture all these without having any high frequency noise. The standard cutoff for ECG monitors of 150 Hz is selected. We designed it using a second order Butterworth filter, which has a coefficients A and B as 1.414 and 1 respectively. Setting the gain to 1 makes the operational amplifier into a voltage follower. We have high pass filter. The high pass filter is used so that frequencies below a certain frequency cutoff are not recorded, allowing a clean signal to be passed through. The cutoff frequency is chosen to be zero point 0.5 Hz. Our resistance used was 318.2 ohm, which was shown in slides in calculation part.
Now let us understand what is the block diagram for the whole circuit. The block diagram for the ECG monitoring system is as shown in the slide. Um First, let us start with the body where the ECG signal is generated. Then the signal will go to the electrodes which pick up the ECG signal. Then comes the instrumentation amplifier which amplifies the ECG signal. Then the notch filter which removes the unwanted noise of 50 Hz. Then the low pass filter which has the cutoff of 150 Hz. Then is the high pass filter which um, high pass filter which has the cutoff of zero point 0.5 hertz. Then we have the our microcontroller ESP32 which digitizes the ECG signal and send it to our MATLAB part. Then we have MATLAB which processes the ECG signal. Then we display the signal which shows the processed ECG signal. This block diagram represents the signal flow in the ECG monitoring system, showing how the ECG signal is acquired, amplified, filtered, digitized, processed, and displayed.
Moving on to the simulation results, we first conducted a transient analysis of the whole circuit. The gain we observed was 1000 and we used an input of 10 millivolts at a frequency of 10 Hz. In the frequency analysis, we found that the minimum and maximum input range was between zero point 0.5 millivolts and 28 millivolts. The bandwidth of the system is from zero point 0.5 Hz to 150 Hz with a notch filter specifically designed to remove the 50 Hz noise. Bandwidth, which refers to a range of frequencies that a system can actually process. We also measured the slew rate of the system, which is zero point 0.4 volts per millisecond. The slew rate is the maximum rate of change of the amplifier output voltage. It tells us how quickly the system can respond to changes in the input signal. In this case, it indicates that the system can respond quickly to changes in the ECG signal. Next, we analyzed the distortion of the circuit, which is the amount of variation of output waveform from the expected waveform. This can be caused by factors such as incorrect biasing, large input, large capacitances causing phase change, or clipping. We found that the total harmonic distortion of our circuit was 7.4%. THD, which is a measure of amount of harmonic distortion present in a signal compared to its fundamental frequency, and a lower THD indicates lesser distortion in the output signal.
Next, we have the hardware result of the circuit that we design in hardware, as shown in the plot below. This is the output of a sine wave with 10 millivolts input of 10 hertz. The yellow signal that we can see is our input signal, and the green wave that we can see is our output signal. And as we can see, the for the 10 millivolts input, the output is almost 10 volts. So we can say the gain of our whole circuit is 1000. And on the right side of the slide we can see the Bode plot or the frequency analysis of the circuit. And as we can see, there is the notch filtering at about 50 hertz, and for 150 hertz we have some low pass cutoff. So this was our frequency analysis. And again, this is the actual ECG signal that we tested in the lab. And the yellow one is the unfiltered signal while the green one is the filtered signal. And as we can see, there is a clear cut ECG signal with the QRS waveform. So this was our final ECG signal as captured on the DSO.
So, after receiving the signal from hardware and transmitting it through ESP32, there was still some noise present. So, we followed some steps to filter the signal in MATLAB. So, what we did was first we tried to remove the low frequency components. In order to do that, we first had to take the FFT of the ECG signal which we captured in a frequency domain. Now we try to remove the low frequency components. After removing the low frequency components, we change it back to time domain using inverse FFT. Secondly, we find the local maxima using windowed filter in order to get the RR peaks and so that we can calculate the heartbeat. So we found the local maxima using windowed filter, setting its size to be approximately 1700. So after using this windowed filter, we removed small values stored and tried to store the significant ones. So after storing significant values, we plotted the signal, and still there was some noise present. We could not filter it out nicely. So we again adjusted the filter size and repeat step 2 and 3. So finally we got a smooth signal with a filter size approximately setting it to be 1300. So after following all those steps, as you can see, the first one is our original ECG signal which we received through ESP32. Secondly, this is our FFT filtered ECG signal where we have removed the low frequency components. And this third plot is where we have passed it through a window filter. Fourth one is we try to detect it ECG signal peaks. Fifth one is again we adjusted the filtered size and tried to filter it more so that we could get a proper ECG signal and without noise. Sixth one is the final detected peaks of our circuit with adjusted filtered size. So here is our MATLAB processing final ECG signal. Clearly there is a clear difference between our received ECG signal through ESP and this MATLAB filtered ECG signal. Here we can clearly identify the peaks of our ECG signal with very low frequency components being filtered out and low presence of noise.
During the development of our ECG monitoring system, we encountered several challenges that we had to overcome. One of the major challenges was related to the transmission of the ECG signal wirelessly. As we needed a large number of samples for an accurate ECG signal, the transmission part proved to be challenging. We had to ensure that the wireless transmission did not introduce any interference or noise that could affect the quality of ECG signal. Another challenge we faced was determining the appropriate gain and cutoff values to use in the circuit. It was important to find the optimal settings to ensure that ECG signal was amplified and filtered effectively while minimizing any unwanted noise or interference. In addition, we faced challenges when processing the ECG signal using MATLAB. We had to determine the optimal window size for detecting peaks in the ECG signal as well as optimal threshold for peak detection. This required careful consideration and experimentation to ensure that the processing was accurate and reliable. There are several proposed improvements that can be made to the ECG monitoring circuit design. One possibility is to modify the circuit to operate with 12 lead electrodes, which can provide more comprehensive and accurate results at the cost of increased hardware complexity. Another potential improvement is to use a Raspberry Pi microcontroller instead of ESP32, as this could provide better data transmission. However, due to cost constraints, we continued with the ESP32 for our prototype. In addition to measuring the heart rate, the ECG signal can be processed to identify certain cardiac diseases. There are a lot of potential for further development and improvement for this circuit, and we plan to continue exploring ways to make it more robust and accurate. Looking ahead, we plan to address the current drawbacks of our prototype and improve the transmission of biosignals over a large distance with less error rate and more accuracy. We also aim to modify the FIR digital signal further to enhance its efficiency in noise reduction.
In conclusion, our project has demonstrated the feasibility of using a low-cost and efficient ECG monitoring system based on the ESP32 microcontroller. The use of power line modems for communication provides an economical and convenient method for chronic patients to monitor their health. The design filter effectively removes noise from the ECG signal, making it more accurate for diagnosis. The cost of this prototype is significantly lower than the existing techniques such as Bluetooth or LAN. Overall, our project provides a promising solution for remote ECG monitoring that can benefit patients and healthcare providers alike. This we come. So with this, we are concluding our project. Thank you.
So we have connected the probes or the electrodes to the three terminals. One is at the right hand, one is, and the two other are at the legs. One at the right and one is at the left. And the three electrodes are connected to the two inputs of the instrumentation amplifier, and one is at the ground. And the instrumentation amplifier is followed by the notch filter, then high pass filter, then low pass filter. And as you can see, this is the ECG signal that we are capturing live of my friend, and the readings that we are getting are pretty nice. There is not that much noise, and there is actually the QRS wave we can see.